Okay, so section 9.6 deals with functions and surfaces. Functions and surfaces. So a function of two variables. So you're used to functions of one variable, right? You're used to functions of one variable, a function of x. But now we have functions of x and y. We have functions of two variables. Okay, so when you have a function of two variables and you want to graph the function, what's the function going to be? What would it have to be? For if your domain is in the xy plane and you have a function that's a function of some domain in the xy plane, what would the function have to represent geometrically? Well, it would be you would need three dimensions. Put it this way: if you have an x, if you have a function of x and y, what's the only variable left? If you're dealing in three dimensions, z. Good. That's right, Eric. That's right, Robin. Naima. Good, Jamal. Ryan. Z is a function of x and y. So when you evaluate functions of x and y, when you evaluate a function of x and y, you're computing a value of z. And you're going to actually graph a surface. And they say here, we often write z as a function of x and y to make explicit the value taken on by f at the general point xy. So the domain has to be a subset of the xy plane. Okay, and of course, anytime you learn about functions, you think about domains and ranges, So like, for instance, if you have a function that equals 4x squared plus y squared, okay, the range of that function is going to be from 0 to infinity, because that function, 4x squared plus y squared, always is positive for any xy values. And of course, the domain would be the entire xy plane, because there's no like x and y could be any value, it's allowed. However, if you have something like this, like on example 2, part A, and then there's a part B, but f of xy equals the square root of x plus y plus 1 divided by x minus 1, if you have that, then, well, they ask, evaluate f of 3 and 2. You just substitute 3 and 2 in for x and y. That's easy to evaluate. But the domain, because you have a square root in the numerator, there's a restriction that comes with a square root, and you have a denominator x minus 1 that you can't let equal 0, that's going to, together, you use both of those pieces of information to determine your domain. And the domain requires, then, that x plus y plus 1 be greater than or equal to 0, so that you have the square root of a positive number in your numerator for that function. Okay. And that x cannot equal 1. So that would be your domain. That would be your domain for this example 2, part A. F of xy equals the square root of x plus y plus 1 divided by x minus 1. Graphically speaking, this is a picture of your domain. This is a picture of it. Okay, right here. You have an asymptote at x equals 1, and all the points above the line, well, x plus y plus 1 equals 0. That means y equals negative x minus 1. That's the line, and all points above it would be allowed. So that's an example of a domain of a function. Okay, and And one more thing too, you might wonder, well, why do we need to learn about functions of two variables? Well, they have a nice example in example 3. They talk about wave heights in feet on the open sea. Okay. So wave heights in the open sea are determined, they're a function of, hold on here, a function of the wind speed. How many have experienced that? Maybe. Wave height, you know, I mean, the more the wind, the greater the wind, okay? I mean, looking at the table here, well, the table is, they have a V and a T. T is the duration, is the duration and time that the wind has been blowing, and V is the speed in knots of the wind. So what they do is the table, the white values are functions, they're the wave heights, which are functions of both time and velocity. Time of that the wind has been blowing and the velocity of the wind. What seems to be happening to the wave heights as time increases from 5 to 50 hours for the wind, and as velocity increases from 10 knots to 60 knots, what seems to be happening to the heights of the waves? In table 1 here, they increase. That's absolutely right. That good, Robin. Good, Christopher. And you can see that if you were to hold like the time of the wind, like if the wind were lasted 5 hours, if you were to hold that constant and look at and then increase the wind speed from 10 to 15 to 20 to 30 knots to 40 knots and so forth, what happens to the wave heights? Do they go up or down? So I'm saying, you know, stick with 5 hours of wind, and suppose the wind speed were to increase. Well, I want to say, if the wind speed, if you have a 5 hour wind, and let's say, well, I want to be careful. Let's say you have 2 instances: a 5 hour wind where the wind is 50 knots, and a 5 hour wind where the wind is 60 knots. Which is going to produce larger wave heights? The 50 knots or the 60 knots? The 60 knots. Yeah, thank you, Ryan. Thank you, Deodath. So, you know, it's necessary. You've learned about functions of one variable your whole life, but oftentimes having one dependent variable is not enough. Sometimes you need multiple dependent variables, and this is an example. You can much better model the wave heights by treating them as functions of both the duration of the wind and the wind speed. And that's what I wanted to mention. That's my intro into section 9.6. Are there any questions? Okay, thank you, Deodath. Well, I'll stop the